Hello, this is Stefan again from schristoph.online. Today we will walk through my latest blog post, Give Every Agent Its Own Computer with AWS Lambda MicroVMs. The idea is simple: every job, user or AI agent gets its own isolated stateful sandbox in a single API call. The post opens with an idea I picked up at a machine learning conference last year. Every AI agent should get its own computer, its own place to run code, keep some state, and not step on anyone else's work. The catch was always operational. Real isolation meant standing up and babysitting infrastructure, so the idea sat in my head with an expensive footnote attached. Then on the 22nd of June, AWS shipped the primitive that makes a computer per agent a single API call. This is the launch announcement. It is built on Firecracker, the same virtualization that already powers more than 15 trillion Lambda invocations a month. Run someone else's code, and you want three things at once: strong isolation, a fast start, and retain state. The old menu made you choose. Virtual machines isolate well but take minutes to start. Containers start fast, but share a kernel. Functions start fast, but forget everything between calls. You could wire up Firecracker yourself at the cost of operating your own virtualization stack. You might fairly ask, isn't this just Firecracker, which has been open source for years? What is actually new? Firecracker, the technology, is not new. What is new is the managed primitive image, snapshotting, the dedicated endpoint, auth tokens, suspend and resume, lifecycle policies, all behind a handful of API calls. The value is removing the operational burden, not inventing isolation. The model is image then launch. You bake an environment once, then stamp out cheap, fast copies. You package your app and a Docker file, upload to S3, and create a microVM image. Lambda runs your Docker file, starts the app, and snapshots the fully initialized memory and disk. When a session needs an environment, run microVM resumes from that snapshot, so the app is already running the instant. The call returns. All of this is in the developer guide. It walks through creating an image, running a microVM, and the suspend and resume lifecycle. Each microVM gets its own dedicated HTTPS endpoint that speaks HTTP2, gRPC, and WebSockets, with no load balancer to set up. A natural question: what state survives the suspend, and for how long? Memory and disk are preserved across suspend and resume for up to 8 hours of the session. But this is session-scoped state, not a database. Anything that must outlive the session belongs in durable storage like S3 that your app writes to. To make it concrete, I wired up the smallest thing that proves the point. A driver script asks Amazon Bedrock to write a Python snippet, then runs that snippet inside a per session microVM instead of on my laptop. The microVM is the agent's computer. The clip shows three moves: speed, state surviving a suspend and resume, and a second microVM that starts empty and sealed off. Here's a fair challenge. The demo runs benign model-generated arithmetic. So does isolation actually hold against hostile code? I can't claim to have stress tested the boundary myself. The isolation comes from Firecracker's VM-level separation, a separate kernel per microVM, the same boundary AWS relies on at very large scale. I state it as a mechanism, and the vendors claim, not my own security audit. My demo is small, but the pattern is not a toy. Anthropic's Claude-managed agents use Lambda MicroVMs as a self-hosted sandbox. Anthropic hosts the model, but each session's tool calls run inside a microVM in your own AWS account. On infrastructure you control, you decide what is installed, what network it reaches, and which resources it can touch. This integration is documented. A session-started webhook hits a launcher in your account, which calls run microVM. Your worker runs the tool calls and posts results back. Even the secrets are handled carefully. Your Anthropic key stays in AWS Secrets Manager and is read by the microVM's execution role at runtime, so it never travels through the launcher. And there is a working reference implementation on AWS samples. That is the part that made the launch click for me. The same primitive backs my 50-line Bedrock demo and a frontier model platform's production agent sandboxes. Two things cost me real time. First, a trust policy mismatch. The build role's source ARN condition had to match the image ARN's colon form, not the /form an IAM example suggested, or the role refused to assume. Second, The minimal base image shipped Python 3.9, so modern union type annotations crash the app at import. A one-line future annotations import fixed it. On cost, you pay for baseline compute while a microVM is running, and only for extra resources when your workload spikes above that baseline up to 4 times during peaks. A suspended microVM drops to a low idle cost. For the actual numbers, I link the pricing page rather than quoting figures that can drift. You might worry, a computer per agent sounds expensive at thousands of concurrent agents. It is real money while busy. The mitigation is suspend and resume. An idle microVM drops to a low idle cost, and bursty interactive work spends most of its wall clock time idle. The honest framing is cheap, while idle, build while busy, not free. If you want to try it, the demo is small on purpose. A Flask sandbox app with its lifecycle hooks, a Docker file, and a Bedrock to microVM driver. Enough to launch a microVM, have a model write code, run it in isolation, and watch state survive a suspend. The code is on GitHub in my Schristoph blog samples repository. Clone it, point it at a region where microVMs is available, and give your agent a computer of its own. The idea that stuck with me at that conference turned out to need just one API call. Thanks for listening. I hope this was helpful. If so, you can reach out on LinkedIn directly or head to my blog at schristoph.online. Let's keep in touch. Take care.